Hi dear students. Dear students, last in the last lecture we discussed about the rotational spectra of rigid diatomic molecule, and in that lecture we tried to discuss the equation for moment of inertia for the rigid diatomic molecule as well as the energy of the energy levels of rigid diatomic molecule. Dear friends, in this part of the video we are going to talk about the frequency of the rotational lines of the rotating molecule, and last time we discussed about the microwave radiations are responsible for the rotational motion of the rigid diatomic molecule. That's why this rotational spectra is also called as the microwave spectra. So dear friends, today in this part of the video we are going to talk about how we can calculate the a frequency of the rotational lines of the rotating molecule or the rotational energy levels. So this is the energy, rotational energy of the energy levels in the rotating molecule S square upon 8 pi square into I into J into J plus 1. This J is called as the rotational quantum number. A rotating molecule is having the permanent dipole moment because this is the necessary condition for the molecule for the rotational motion or the rotational spectra, and hence it generates electric field which can interact with the electrical component of micro radiation, and that leads to the micro spectra. And it is also observed that only those rotational transitions are permitted in which the rotational quantum number increases by 1, and that is delta J is equal to 1. Delta J is equal to 1, and this is the actually selection rule for the rotational spectrum. Delta J is equal to plus or minus 1. For transition from J equal to 0 to 2, delta J is equal to 2 are not possible, are not allowed in the rotational spectra. So let us consider the transition of the molecule from one rotational energy level J is equal to 0 to J is equal to 1, or that is nothing but the J single prime to J double prime, and that's why the energy difference between these two energy level will be Ej double prime minus Ej single prime. And this Ej is given by here with this equation S square upon 8 pi square into I into J into J plus 1. So we can write this same equation for the J single prime as well as J double prime, and if we put values in this case Ej double prime minus Ej single prime, then S square upon 8 pi square into I into J double prime into bracket J double prime plus 1 minus S square upon 8 pi square into I into J single prime into J single prime plus 1. So here we have this term as a constant. So in the bracket there will be only this one, okay, but the difference between the two energy levels, rotational energy level J double prime minus J single prime is equal to 1. Therefore from this J single prime will be equal to J double prime minus 1. So if we will put instead of J single prime as J double prime minus 1, then definitely we will get this equation, that is J double prime as it is J double prime plus 1 minus J single prime is replaced by J double prime minus 1, so it should have the bracket and J double prime minus 1 plus 1 as it is. So here after solving all this, definitely this plus 1 minus 1 will get cancelled, and this if J double prime square, it is also square, so there will be plus J double prime minus plus, that is this minus plus will be in J double prime, and there will be the only one equation S square upon 8 pi square into I into 2 into J double prime. So according to, so this is the energy difference between the two energy levels which are separated by J delta Ej energy. So according to Planck's quantum theory of radiation, the energy changes are quantized by the equation. The energy difference between any two energy levels is always equal to delta E is equal to h mu, which is equal to h mu bar into C. This is the wave number. Mu is the frequency, mu bar is the wave number, and here this is also there is a difference, and this is also there is a difference. So if we equate this equation, definitely we will get this, and if on rearranging this equation, it means this H and C, or by dividing this equation by SC on both sides, we will have the equation for the frequency in terms of wave number as 1 upon S into C into S square upon 8 pi square into I into 2 into J double prime. This H will get cancelled. Definitely there will be only one H. So H upon 8 pi square I into this C into 2 into J double prime. So here this H is constant, pi is constant, I, C all are constant, and instead of this constant we will take the another constant B, and this B is called as the Jerome constant, or it is also called as the rotational constant, which is equal to H upon 8 pi square into I into C. So if we put this B here, so definitely the frequency in terms of wave number will be given as, that is mu bar is equal to 2 into B into J double prime. So here as B is equal to this, means we can write this equation for the I also. Now we will talk about the transitions from J double single prime to J double prime. Suppose this is the first transition from J single prime to 0 to J double prime 1. So J single prime is equal to 0, but J double prime is equal to 1. And if we put this equation in the equation number 1.1.20, B is equal to 1 means mu bar will be equal to 2B. If for the second transition from 1 to 2, J double prime will be 2, and if we put this here, so it will be 2 into 2 into J double prime, so it will become 4J prime, 4J double prime. And for the another transition from 2 to 3, J double prime is equal to 3, and if we put this 3 into 2 becomes 6, so it will be 6B. And if we calculate the energy difference between either these two or these two, 4B minus 2B is equal to 2B, 6B minus 4B is also 2B. So energy difference between, or the frequency difference between the consecutive spectral line is always equal to 2B. And definitely, so delta mu bar is equal to 2B, therefore B is equal to the delta mu bar divided by 2, and it is equal to H upon 8 pi square into I into C. So yeah, this is the simplification here. In this way, we are able to calculate the energy of each rotational energy level with the help of this equation. And here, the equation for the rotational energy level, or the energy of rotational energy level, is given by S square upon 8 pi square into I into J into J plus 1. If we simplify this, then S square can be written as H into H. So divide by C and multiply by C. So here it is H upon 8 pi square I into C. So this is the B into H into C. So for the energy of rotational energy level, we are getting this equation E is equal to BSC into J into J plus 1. So for the transition, J is equal to, so if we, for the first 0th energy level, J is equal to 0, so energy will be also 0. For J is equal to 1, means the first energy level. Then this B is equal to 1 means that is nothing but the J is equal to 1 means 1 plus 1 2, so it becomes 2 BSC. For the J is equal to 2, that is 2 into 2 plus 1, 3 into 2 6, so 36. In this way we can go for the higher values of J, and in this way we are getting the energy of each rotational energy level 0, 2, 6, 12 and 20 BSC. It means that the first energy level is located at the 0, second is located at the 2, and third is located at the 6, next is located at the 12. It means that as the values of J goes on increasing, the energy of energy level also goes on increasing, but the difference between the successive energy level is also goes on increasing. This energy difference is 2, this energy difference is the double of this 2, it is 4 times of this BSC, and now it is in this way, the energy difference between the two successive energy level goes on increasing with the value of J, and this is the frequencies difference, or this is the difference in the frequency of the lines that remains constant. Here there are some conclusions from the rotational spectra. The first one is the selection rule. Here it is also observed that the transition occurs in accordance with some specific rules, and these specific rules are called as the selection rule. So what is the necessary condition, essential condition for the molecule to show the rotational spectra? First is that the molecule must have permanent dipole moment. Then the molecule will show rotational or the microspectra, and the molecule will be called like the microwave active. That's why the molecules like carbon monoxide, HCl, these all are microactive, and the symmetric molecules such as hydrogen, oxygen, chlorine, nitrogen, all are not having dipole moment, means their dipole moment will be zero, and that's why these are called as microwave inactive. Second case is that only those transitions are allowed for which delta G is equal to plus minus 1. For absorption spectra, delta G is equal to plus 1, and for the emission spectra, delta G is equal to minus 1. But this delta G is equal to plus minus 1, it is the condition for the transitions in the rotational, or in the this is the condition for the rotational transitions in the rotating molecule. So this is just regarding, there are some limitations of the rotational spectra. It is observed for those molecules in which the permanent dipole moment is present. It means that molecules without permanent dipole moment cannot be studied with the rotational spectra. Homopolar molecules do not give the rotational spectra as their dipole moment is zero. Again, linear non-polar molecules like carbon dioxide are microwave inactive. Non-linear non-polar molecules like methane, benzene, then carbon tetrachloride are also microwave inactive, as their dipole moment is zero due to symmetrical geometry. So this is all regarding with the limitations of microspectra. Again, it is also observed that if the atoms in the molecule are replaced by their isotope, that also shows some effect on their rotational spectra, and the presence of isotope in the molecule will bring about the change in the reduced mass of the molecule, though the internuclear distance remains unchanged. This will bring about the change in the moment of inertia and the rotational energy, and hence the frequency separation of successive lines in the rotational spectra of the isotopic molecule will not be same as that of the original molecule, and hence we can say that the presence of isotopic atoms may modify the frequency of spectral lines or produce supplementary lines. Due to the presence of isotopes of carbon 12 and carbon 13, the lines in the rotational spectrum of carbon monoxide were found to be modified. These are different, and the effect of isotopes on the rotational spectra was first observed by Imes, and the theoretical list was put forward by Milker. So the rotational constant B is inversely proportional to moment of inertia, and hence heavier isotope will have the larger moment of inertia, and definitely will have the smaller value of B, as B and I, these are the inversely proportional. The frequency separation of successive lines also depends on B, will be smaller for the heavier isotopic molecule than the lighter isotopic molecule, and the small difference in the frequency separation have been utilized to determine the isotopic masses of the molecules, and the isotopic abundance can be determined from the intensity of the rotational spectral lines. Suppose we will consider here the two isotopic molecules A and A prime. Their reduced mass will be mu and mu prime, having the moment of inertia I and I prime, and their rotational constant will be B and B prime. As B is equal to h upon 8 pi square into I into C, so therefore B prime will be h upon 8 pi square into I prime into C. So B upon B prime, all this will cancel, only I prime upon I, because B and I, these are the inversely proportional, but I is equal to mu r square, moment of inertia. Therefore, I prime upon I is equal to mu prime upon, so we can conclude B upon B prime is equal to mu prime upon mu. And this B is equal to, therefore, as delta mu is equal to 2B, so we can write 2B is equal to delta mu bar, and 2B prime is equal to delta mu prime bar. 2 will get cancelled, and only we will have this equation. So this is the effect of isotopes on the energy levels of rotational spectrum of the carbon monoxide molecule. So this is the normal molecule, and this is the isotopic molecule. So here you can say that the energy difference between the two energy levels goes on decreasing in case of a heavier molecule, and it remains as it is in case of a lighter or the normal molecule. So this is the dotted line indicates the frequency of lines for isotopic molecule, and this continuous line indicates for the C12. So this is all about. This is one numerical. Yes, sister, numericals can be asked to you. The frequency separation between successive line in the pure rotational spectrum of HBr is given 1.7 into 10 raised to 3 per meter. Calculate the equilibrium internuclear distance in the molecule. The internuclear distance can be calculated with the help of formula given by the moment of inertia. I is equal to mu r square. That's why r is equal to under root of mu of I upon mu. But for the purpose, we will require the I, and this I can be calculated with the help of this equation, h upon 4 pi square into c into 2b, or I is equal to h upon 8 pi square b into c. So this is, but how this b is calculated, 2b is calculated. Here delta mu is equal to 2b, delta mu is equal to 2b, and the value of delta mu is given to you, and this is equal to 1.7 into 10 raised to 3. Sometimes from this we will also able to calculate the rotational constant, that is b. So this type the numericals can be asked to you in the examination. If the separation between successive lines in the pure rotational spectrum is given, then they can ask you the value of rotational quantum numbers. Sorry, rotational constant b. So this is the way. So dear friends, in the next part of the video, we would like to discuss about the vibrational spectrum of the molecule, diatomic molecule. So we'll resume again in the next part of the video to discuss about the vibrational spectrum or the vibrational spectroscopy of the rigid diatomic molecule. Thank you very much.